In this video, we're going to take a look at the kinematics of circular motion, and this is going to be perspective number 1. And in order to set up and establish just our basic models, or you might call them equations, some of these fundamental ideas, we're just going to look at an object which is moving in a circle at a constant speed. Now, we know that speed is defined by d over t. And we could write this with our vector symbol, but we're taking the absolute value of it. This is going to be distance, not displacement. And of course, t is the time interval to cover that distance. When we're talking about something in circular motion, we're talking about it moving in a circle. The object is going to have to go all the way around this circle 360 degrees. Now, the distance that it's going to travel is just going to be the circumference of the circle. So that means our speed is equal to circumference divided by the time interval. Now, if it's moving in a constant speed, it's going to take the same amount of time to go around the circle every time it goes around. Instead of writing a lowercase t, we're going to write a capital T, which represents a constant, which we call the period. So capital T is the period, and this is the time to go around once. Now, the period is not the same thing as time, because this time is a variable. When we write a lowercase t, it's a variable. So, for example, the period to go around this circle might be 1 second. Okay, so we would say t is equal to 1 second. But if I say that this object is going to go around half the circle, how long would that take? In that case, t would be equal to 0.5 seconds. So you see, t represents the variable, where capital T represents the constant. So we get v is equal to circumference divided by the period. And now we just rewrite our circumference as 2 pi r divided by t. R is the radius of the circle. And again, t represents the period, which is the time to go around once. We've talked about velocity as being a vector, and that anytime the velocity changes, you have an acceleration. And there are two ways that we can change velocity. Velocity can change because the speed is changing, and that's what we studied in Unit 1 with kinematics. We wrote acceleration was equal to delta v over t. And in fact, acceleration is still going to be defined as delta v over t, as we're going to see in a minute. But that's not the only way to create an acceleration by changing the speed. You can also create an acceleration by changing direction. And that's really what circular motion is all about. We must have a net force because we have an acceleration, and the acceleration is a direct result of the changing direction. Now, without any kind of proof, what we're going to say is that centripetal acceleration is just equal to the speed, or we could say v tangential squared, divided by r. Now, what we're going to say here, though, is we're going to use the RTZ coordinate system, and that positive is always towards the center. This r is still the same radius of the circle. And so just as a quick note, we're going to say that a centripetal is the acceleration due to changing direction, and a tangential is the acceleration due to changing speed. Now, just real quick, make sure we label our diagram here. The center of the circle is here. The distance from the center of the circle to where the object is located is going to be the radius, which we're calling r. And again, this object is moving in a circle, so r is going to remain constant. What I want to do right now is prove to you that the acceleration is the result of a changing direction, and I want to make sure that it's clear that the acceleration is pointing towards the center of the circle. Okay, now what I have here is I've drawn a circle and I've made it such that the center of the circle can easily be located with these lines that I have going horizontally and vertically. And we're going to use those in a little bit. Now we all know, or we should know, that the acceleration is equal to the change in velocity over the change in time. And that's by definition. That is going to be true for changing speed, and it's also going to be true for changing direction. So we could rewrite this as acceleration is equal to v final minus v initial divided by t. Now, my only purpose here with this particular diagram is to prove what the direction is going to be. And as a result, what I'm going to do is I'm going to ignore the time component, because the time component is a scalar, and all it does is take the quantity of v final minus v initial and it scales it up or down to a bigger or smaller number, which ultimately we call the acceleration. So I'm just using this to establish direction but not magnitude. So what we're going to do is this. We're going to say we have a particle which is moving in a circle, and we're going to say that it's moving in a clockwise direction. So the velocity is going to remain the same, and for simplicity, I'm going to make the velocity 3 blocks long. And that's at this point in time. At this point in time right here, it's still moving with a velocity that's 3 blocks long. It's just now it's pointing straight down. So if I want to determine what the acceleration is going from this point to this point, so this is v initial and that's v final, all right, so this is v initial, this is v final, then what I need to do, find this quantity right here, v final minus v initial. So we're just going to do some head to tail vector addition. We're looking for v final minus v initial. Well, v final minus v initial is the same thing as v final plus a negative v initial. If v initial points to the right, then a negative v initial points to the left. And so we know that it's going to be 3 blocks long. And I'm just going to actually just copy it from up here. I'm going to do this. I'm going to go in this direction, and that's negative v initial pointing to the left. So I'm going to drag this vector down to here. Because remember, I'm trying to do v final minus v initial. Now, the resultant of this head to tail vector addition is the acceleration. That's what we see here. Acceleration is equal to v final minus v initial, and the resultant of v final minus v initial is the acceleration. So let me draw in my resultant vector. My resultant vector is going to go from the starting point of the diagram to the ending point. And so this yellow dotted line is my acceleration vector. Now I've got a question for you. We said at the onset that the acceleration points towards the center of the circle. And very clearly we do not have our acceleration pointing to the center of the circle. So what I want to know from you is why. Why is the acceleration not pointing towards the center of the circle? Okay, believe it or not, the answer is quite simple. It's all based on our definition of this acceleration here. And this acceleration is an average acceleration, not an instantaneous acceleration. And the average represents the midpoint of the high and the low. And so the key here is that it's midpoint. And so what I need to do is I need to take my acceleration vector and place it at the point which is halfway between these 2 points, because that's what represents the average. And that's going to be approximately right here at this location. So I could just follow that diagonal there. And so there's my acceleration vector. Now, very clearly that appears to be pointing towards the center of the circle. And what I'm going to do now is just highlight the white lines that I have here I'm going to bring those forward. And there we have it. You can see that my acceleration vector is very nearly towards the center of the circle. And how close you get to the center, of course, is dependent upon just how careful you are whenever you draw the diagram. Now, I want to do this one more time to show you that it doesn't matter really what the time interval is, and maybe this might even be a little bit easier for you to visualize. But we're going to do the same thing that we did before. We're just going to say the acceleration is 3 blocks long, or the velocity is 3 blocks long, and we're going to take the two extreme points so that everything is in a one-dimensional line. So we've got the initial velocity points to the right. We've got the final velocity is going to point to the left, and it's going to be exactly at the bottom. And it appears that my final velocity really is, well, it's close enough. Okay, now we're going to do the same thing. We're going to do v final minus v initial. And so here we have v final minus v initial is going to be this vector diagram. Once again, we're going to go from here to there, and we add them up head to tail, and the acceleration vector is going to be the resultant of this subtraction, or this addition if you want to think of it as addition. And so the resultant is going to be from where we started to where we ended. There's our resultant vector. Now remember, all we're interested in is direction. Okay, so what is the midpoint between this extreme and this extreme? It's going to be this line right here. Okay, because remember, this is average acceleration. So we place this at the midpoint, and very clearly now it is passing through the center of the circle. And that's all I wanted you to see through this particular diagram, that the direction does point towards the center of the circle. Even though the velocity doesn't change, we still have an acceleration, and that acceleration is a direct result of the changing direction. Now, we've already talked about the acceleration that an object can have can be the result of two different things. We said that it could be the result of atangential, which basically means we have a changing speed, and then we have acentripetal, which means we have a changing direction. So is it possible that an object can have both a tangential acceleration and a centripetal acceleration? The answer to that, of course, is yes. If you're riding a roller coaster, then as you go up and around a loop, you're going to slow down on the way up, and you're going to speed up on the way back down. But not only is your speed changing, because you're moving in a curve or an arc, basically we're looking at circular motion, and there's a changing direction. Therefore, you have both a tangential acceleration and a centripetal acceleration. So if we do this in terms of a diagram, then you might have a car or some other object right here that's going around a curve. And we're going to say that the velocity is in that direction. It's moving straight up. So the tangential acceleration is going to be tangent to the path of the circle. So we have atangential points in that direction, and acentripetal points towards the center of the circle. So what is the total acceleration? In order to find the total acceleration, we're just saying that a total is equal to a tangential plus a centripetal. When you add this up, you're basically looking at a head-to-tail diagram if we take a graphical approach to it. So we have a total is going to be equal to a tangential plus a centripetal. And drawing a head-to-tail diagram, we get a tangential head to tail with a centripetal, and that's going to leave us with a total being the hypotenuse of a right triangle. So anytime you have a situation where an object is accelerating both tangentially and centripetally, all you have to do is use the Pythagorean theorem to find the total acceleration. Okay, so just like before with whenever we looked at vector addition, the Pythagorean theorem is only going to give you the magnitude, or how large the acceleration is. This is what you would experience, what you would feel if you were, say, on a roller coaster or in a car going around that bend. So A total, the magnitude of A total is just the Pythagorean theorem. If you want the direction theta, then theta is just going to be the same way we always do it. It's going to come from the inverse tangent of the vertical component, which is, in this case at least, a tangential, divided by a centripetal. All right, so you just need to have some type of a reference frame for establishing where theta is measured from and what the actual direction is. But in our case, in this diagram that we have over here, we would say that the total acceleration is pointing in this direction here. Okay, now, one of the last things I want to talk about here has to do with why you experience what you experience when you're driving around a bend in a car. And looking at this scenario, let's just say we're in a car and we're driving not counterclockwise like we were earlier, but let's change that direction to clockwise. So let's say that we're now moving in the down direction, so I have room to write. Okay, so the car has followed this path to get to this point. And as you're going around the turn, you feel like you're getting thrown to the outside edge of the car. So if you're sitting right here inside the car, you feel like you're being pushed in that direction. Now, you're not actually being pushed in that direction, and the reason why is because of inertia. As you go around this bend, tangent to any point, your tendency is to want to move in a straight line. In other words, if this were an icy surface, then the car at this point in time, because its velocity is straight down, if there were no more friction to keep the car going around the bend, then the car would follow a straight line path like this. All right, and that's what's happening with your body. As the car goes around the bend, the car is following the curved path, but your body wants to follow the straight line path. And so what's really happening is the car is undercutting you. It's coming towards you as you are trying to stay in that straight line. Okay, the point of this video was just the kinematics of circular motion, understanding speed and acceleration and direction. And so we have speed as being defined as distance over time, and because we're moving in a circle, we're always going to use the circumference of a circle in our equation, which is 2 pi r. T is the period, capital T is the period, which is a constant, not to be confused with little t. So it's extremely important that whenever you write out your variables that you are using the appropriate letter. If we learn in class it's a lowercase t, then you use a lowercase t. If it's a capital T, you use a capital T. One mistake that I see all the time that goes for many weeks and months into the school year is that students will use a capital A for acceleration, and it should be a lowercase a. You should never ever use a capital A to represent acceleration. It has other meanings in physics. We just have 2 pi r is always going to be the way we find the distance around the circle. A centripetal is the acceleration, which is the result of a changing direction, and without any kind of proof, we're just stating that it's the tangential velocity squared divided by the radius. And that a tangential acceleration is just changing how large the speed is. Then we went and we looked at centripetal acceleration. How do you go about finding the direction? And to do that, we used the definition of acceleration, which is just delta v over t, or v final minus v initial divided by t. And because we're only interested in the directional component, we were able to ignore the time component, which is a scalar. And that scalar quantity, when we divide by this scalar quantity, it's just going to make this value larger or smaller. And so we were able to draw a head-to-tail diagram based on our definition of acceleration using constant speed, and what we were able to demonstrate is that the acceleration always points towards the center of the circle. The first time we did this, the acceleration pointed towards the center from here, and then the second time we did it, it pointed towards the center from here. And that when you draw this diagram, the acceleration has to be placed at the average location because it's an average acceleration. Then finally, we talked about total acceleration, and the total acceleration is going to be the vector sum of the tangential plus the centripetal acceleration. You would experience an acceleration if you're going around a circle with a changing speed. You're going to experience an acceleration which is the combination of the two. To get the magnitude of that acceleration, you just use the Pythagorean theorem because centripetal and tangential acceleration are at right angles to each other. And then finally, if you want to get the direction of that acceleration, you would have to use the inverse tangent function. Now, the last thing that I want to say about total acceleration is this is something that we're not going to put a lot of emphasis on in this course, but you do need to be aware of it.